Let me begin with just an overview of what we're going to do, what the rough plan is. So what we're going to do is we're going to begin by talking about what's called the discrete Gaussian free field. And I'm going to abbreviate this by DGFF. Then after that, we're going to do the continuum Gaussian free field. And this I'm just going to refer to as the GFF. Then what we're going to do is we're going to describe what are called local sets for the Gaussian free field. And then finally, at the end, we'll go over the various couplings between SLE and the Gaussian free field. And one thing that I want to emphasize is that most of this is going to be, most of this course is going to be about the continuum Gaussian free field, local sets, and its connection with SLE. The reason that I'm going to begin today with the discrete Gaussian free field is that when you work with the continuum Gaussian free field, there are a number of kind of annoying little technicalities that you have to deal with, and these are not present when you work with the discrete Gaussian free field. But at the same time, it's possible to give a treatment of the discrete Gaussian free field which is completely parallel with the treatment one wants to give for the continuum Gaussian free field. And let me just also mention that not to shortchange the discrete Gaussian free field. This is also a very important object in probability because just like the continuum Gaussian free field is connected to many other objects in probability, so is the discrete Gaussian free field. In particular to random walk. And as we'll see, random walk is going to enter into the picture right at the beginning. OK, so here's the setup. So I want to assume that I have a graph, and my graphs will always be written with this calligraphic G. And whenever I write the vertex set for my graph, I'm always going to decompose it into two different parts. There's going to be the interior vertices, which are always V, and the boundary vertices I'll indicate with the symbol partial V. OK, so this is always going to be a finite graph. And it's going to be connected. And I'm also always going to assume that the boundary set of vertices is non-empty. OK, so what is the discrete Gaussian free field? So the discrete Gaussian free field on this graph, this refers to the measure, or probability measure, on functions. And these functions are defined on the vertices of the graph, and they're real valued. And this measure is described in terms of its density with respect to Lebesgue measure. And here it is. So you have a normalizing constant, just to turn this into a probability, 1 over z. And then you have e to the minus 1/2. And then you sum over all edges in your graph. And then you take the square of the gradient of your function across each edge, and you add that up. Okay? So this is with respect to Lebesgue measure on R to the size of the graph. And let me also emphasize here that the functions that I'm considering, when you restrict them to the boundary, I'm going to assume for simplicity that they take on the value 0. So this is the 0 boundary discrete Gaussian free field. Okay? And as I said earlier, the sum here, this is over all edges in E. OK, so that's how the discrete Gaussian free field is defined. Let's do just a quick example. So let's suppose that my graph is the one which is just given by the line. So this is just a subset of the integers. And this is 0 right here. And 0 I'm going to take to be the boundary of my graph. And then the rest, 1 up to n, these are going to be the interior vertices of my graph. And the edges are just the usual ones that you get when you take the integers from 0 to n. Okay. Yeah, so in this case, then the density for the discrete Gaussian free field is just given by a normalizing constant. And then you have e to the minus 1/2. And then you sum from I, let's say j, up to 1 to n of h of j minus h of j minus 1 squared. Okay, so it's pretty simple in this case. And one thing to note is that that I just want to really emphasize is that in this case, the random variables psi I, which are given by h of I minus h of I minus 1, if you just stare at this for a second, you'll realize that these psi i's, these are just our IID normal 0, 1. And you can write h of j as just the sum from I goes from 1 to j of psi I. Okay? And because of this, you just observe that the discrete Gaussian free field in this case is just it's just a random walk. Same thing as a random walk with IID normal 0, 1 increments. Okay, so it's a very very simple object. And the way that you should think about the Gaussian free field, or one way of thinking about it on other graphs, is that on other graphs is that it's just sort of the natural generalization, or one natural generalization of Gaussian random walk. Okay, so this is kind of the simplest example that one can consider. All right, so now what I want to do is to start to prove some of the basic properties of the discrete Gaussian free field. And as I mentioned earlier, I'm going to do this in a way which is going to be completely parallel with the way that one establishes the corresponding properties for the continuum Gaussian free field, except there won't be any of these annoying little technical points coming up. And the starting point for that is the following Hilbert space representation of the discrete Gaussian free field. So this is the perspective that makes it pretty straightforward to prove lots of things about it. So I'm going to use the following notation. So I'm going to write nabla f of b this is for a function defined on my graph, and we're going to write nabla f of b for the difference between f of y and f of x, where here b is an oriented edge. Or where B is the oriented edge connecting x and y. So I'm going to write this for the discrete gradient. And I'm also going to define the Laplacian of f at x to be the sum over all y which are adjacent to x. And I'm going to take the difference of f of y and f of x and just sum it up. Okay? So we have the discrete gradient and the discrete Laplacian. And now let me introduce the Hilbert space structure. So to do that, let me start off by defining h of g. This is just going to be the set of all functions on my graph, which take on real values. And I'm going to constrain my functions so that on the boundary set of vertices, they always take on the value 0. And I'm going to make this into a Hilbert space by equipping it with an inner product and this inner product, what you do is for functions f and g, you just define this to be the sum over all edges in the graph, and then you take the product of the gradient of f with the gradient of g. Okay? And well, of course, you might worry that these edges are not oriented, and here I'm summing over gradients. But of course, this product here does not depend on what the orientation of the edge is, because if you flip it, then both of the signs are going to cancel. Okay, so this is my inner product, and this has a name. This is called the discrete Dirichlet inner product. Okay, and then the norm, which is associated with this, the associated norm, I'm going to write with the usual norm sign, and then a subscript nabla. This is just given by the sum over all edges in the graph, and then I take the square of the gradient of my function across that edge. Okay, and this is the Hilbert space that I want to work with. All right, so now let's suppose that we have functions f1 up to fn, and these functions are an orthonormal basis for h of g, and I'm going to be just abbreviating orthonormal basis by O and B hereafter. So these are an orthonormal basis of h of g, and I'm going to set h to be a random linear combination of these basis elements, where the coefficients alpha 1 up to alpha n, these are just IID normal 0, 1 normal 0, 1 random variables. Okay. Okay, so this defines another random function on my graph, and the claim is that this h that I've just defined, this is a discrete Gaussian free field on the graph G. And the reason for this is that just note that if you take the norm of this h that I've defined, then what is this equal to? This is just equal to the sum of the alphas, the sum of the square of the alphas, okay, just by orthogonality. And And the density of this law with respect to Lebesgue measure is just given by a proportionality constant times e to the minus sum of the square of the alphas over 2, because this is just the usual density for n IID normal 0, 1s. And you can rewrite this as e to the minus norm of h squared divided by 2. And that was exactly the form of the density for the discrete Gaussian free field that I wrote right in the very beginning at the top of this board over here. OK. But now, as we're going to see, this representation is very handy for establishing properties of the Gaussian free field. So let's start off with probably the most important one, which is the Markov property. And then after we do the Markov property, we're going to derive the covariance function for the heights of the field. Yeah. OK. Does this just roll?
Oh, just on the.
Oh, just close it. Is that better? Can everybody? OK, great. I can also move this if it's necessary. But all right, great. OK. So yeah, OK. So I'm going to do the Markov property for the discrete Gaussian free field. And then after this, I'm going to derive what its covariance function is. OK. So let's suppose that we have a subset of vertices in my graph, U. Then we say that a function, let's say g, on the graph, this is harmonic on U if the Laplacian, this discrete Laplacian of g, is equal to 0 for all x in U. Okay, so this is what it means for a function to be harmonic. And I just want to point out now, before we do the Markov property, two useful characterizations of harmonic functions. So the first one is going to be the variational characterization. So here it is. So what it says is that if you have a subset of vertices in the graph, and you have a function on the graph which is discrete harmonic, on U, then it's true that among, let's see here, yeah, among all functions on the graph which agree with G outside of U, what do we have? We have that G is the unique minimizer of the norm of the function that just assigns with each function on the graph its corresponding norm. Okay, so this is one way to characterize a harmonic function. And I really like this in the discrete setting, by the way, because the corresponding fact is also true in the continuum. But as we're going to see in a moment, the proof in the discrete setting is very, very short and nice. So yeah, how do you prove this? Well, the first thing is that is just to note that this function, which associates with a function on the graph, its norm, this is convex, strictly convex. And because of this, a function is going to be a minimizer if and only if it's true that it's a critical point. Okay, and what does it mean for a function to be a critical point? It just means that if you take the norm of your function, its square norm, and you differentiate it with respect to its value at any given point in u, so it's true that for all x in u, we have that the derivative of the norm of the function with respect to its value at x has to be equal to 0. But what is this equal to? Let me just write out the formula for the norm again. So we just take the sum of the squares of the gradients. Okay, so that's all that this is. And if you just calculate the derivative now, you just get minus 2 times the sum over all of the edges which contain x of the gradient of f of v. Okay, so all of the terms in the summation which don't contain x drop out, and you're just left summing over the ones that do contain b. And if you think about this for a moment, this is the same thing as minus 2 times the Laplacian of f at x. Okay, and so since this has to be 0 at every point in u, that's the same thing as saying that this function is harmonic. Okay, so this is the first kind of useful fact that I wanted to mention. One consequence of this, of course, is that it tells you that if you prescribe a given set of boundary values, there's a unique way to extend those boundary values harmonically into the interior. All right. Now let me do the second characterization. All right, so for the second characterization that I want to mention of harmonic functions, let me first just remind you what it means for something to be a simple random walk. So let's suppose that capital X is a simple random walk on my graph. And I'll abbreviate this by SRW. On my graph. So just to remind you what this means, this just means that X is the Markov chain on the vertices of the graph where if p superscript x, if this denotes the law under which capital X starts from little x, then we have that the probability starting from x that at time 1 you go to y, this is equal to 1 over the degree of x, where here x and y are adjacent. So again, here d of x is the degree of x. Okay, so this is what a simple random walk is. And what I'm going to do is I'm going to let tau sub u, this is just going to be the first time that that x leaves the set u. Then it's true that that a function g on the graph, this is discrete harmonic if and only if for all x and u we have that the value of g at x is given by the expectation starting at x of g evaluated at where the random walk first exits the set u. Okay, and this is just like for the previous characterization, this is also very easy to prove. So let's just do that. So let's suppose that we have a function f which is in h of g, and we know that f of x is equal to g of x for all x not in u. And we also know that f of x is equal to the expectation starting at x of f of x tau u for all x in u. Then if you just apply the Markov property for x, then what do you get? What you get is that f of x is just going to be equal to 1 over d of x times the sum over all y which are adjacent to x of the expectation starting from y of f of x tau u. And this is true for all x and u. Okay. And if you just rearrange this, this tells you that the Laplacian of f of x is equal to 0 for all x in u. Okay. And this tells you that this function has to be harmonic. All right. Now what we're going to do is we're going to use these things to get the Markov property for the discrete Gaussian free field. Okay, and before we do that, we need just a little bit more preparation. So what I'm going to do is I'm going to define for u a subset of vertices. I need to define 2 more spaces. I'm going to let h superscript harm of u. This is going to be the set of functions in this on the graph which have the property that they are harmonic in U. So the Laplacian is equal to 0 at all points x in U. And I'm going to let H sup of U, this is going to be the set of all functions in the on the graph such that their support is contained in U. So the set of all x such that f of x is not equal to 0, this is a subset of U. Okay. And yeah, the one thing that one needs before proving the Markov property is the following lemma. And what the lemma says is that if you take the sum of h harm of U and h sup of U, then this gives you an orthogonal decomposition of the whole space A, or whole space, sorry, H of G. Okay, and this little observation that's coming is what allows one to give a very short proof of the Markov property for the discrete Gaussian free field. So let's prove this. So let's first suppose that we have a function f, which is in h harm of U, so it's harmonic on U, and we have another function g, which is in h sup of U, so it's supported on U. Then let's compute their inner product. So the inner product of f and g. Remember, this is just the sum over all edges in the graph of the gradient of f times the gradient of g. Okay, so this is just what this is equal to. And okay, and so what do we do with this? Well, you can just apply the summation by parts formula. So here I'm going to apply summation by parts. Which is just a discrete analog of integration by parts. And the summation by parts formula tells you that this is just going to be equal to minus the sum over all x and v of the Laplacian of f of x times g of x. So the Laplacian here is only on f. And this has to be equal to 0. And the reason it's equal to 0 is that the Laplacian of f is equal to 0 whenever x is in U, and where did the eraser go? Yeah, and g is just equal to 0 when x is not in U. Yeah, so this is equal to 0 because the Laplacian of f of x, the first term is equal to 0 for x in U, and the second factor is always equal to 0. Oops, when x is not in U. Okay, and so that tells you that the inner product of these two functions has to be equal to 0, and therefore these two spaces are at least orthogonal subspaces. Now let's show that they span. To show that they span, what are we going to do? We're just going to fix a function f in h of g, and then we're going to let f tilde, this is just going to be the unique solution of the equation given by the Laplacian of f of x is equal to 0 for x in u. And f tilde of x is going to be equal to f of x for x not in u. Okay, so I'm just going to define this function. And based on how I've defined it, just by definition, f tilde, this is in h harm of u, and f minus f tilde, this is in h sup of u. And of course, f is just equal to f tilde plus f minus f tilde. Okay, and that finishes the proof that these two subspaces actually span. All right, so now we can do the Markov property finally for the discrete Gaussian free field. Yeah, so to do this, what do we do? So again, we're going to suppose that U is a subset of vertices in V. And then what I'm going to do is I'm going to let f1 up to fk. This is going to be an orthonormal basis of h sup u. And I'm going to let g1 up to gl. This is going to be an orthonormal basis of h harm u. Okay. And then, excuse me, by the lemma that we just proved here, these two bases together form a basis of the whole space. So then f1 up to fk and g1 up to gl, these guys together form an orthonormal basis for our big space h of g. Oops, need the eraser. And so, if we have a Gaussian free field on our graph, so if H is a discrete Gaussian free field, this is a discrete Gaussian free field on G, then we can write H as the sum of alpha 1 f1 up to alpha k fk plus beta 1 g1 up to beta l gl, where here the alphas and the betas together are IID normal 0, 1. Okay, and this decomposes the free field into two parts. So we have this first part here and this second part here. And let me call the first one H1 and the second one H2. And I have forgotten which one is which. So, right, so the first one, so then H1 and H2 are independent. These are independent. And H1, this is just a discrete Gaussian free field on the subgraph, which is formed by taking its boundary vertices to be given by all of the vertices in the graph which are not in U, and taking its interior vertices to be those that are in U. Okay, and also in H2, this is a harmonic function. This is harmonic on U. Okay, and this this statement here basically is the Markov property for the discrete Gaussian free field. So what I want to do now is just state this this property in the way that people usually think about it when you actually use the Markov property for the Gaussian free field. So here's how you usually think about it. The way that you usually think about it is that you just say that the conditional law of your discrete Gaussian free field H, given its values off U, can be expressed as the sum of a discrete Gaussian free field on U plus the harmonic extension of its boundary values plus the harmonic extension of the values of H off U to U. Okay, and then this is just another way of saying exactly the same thing that I just wrote here. Okay, so that's the Markov property for the discrete Gaussian free field. Now, in the last 15 or 20 minutes or so, I'm going to derive the covariance function. So we want to derive the covariance function for the discrete Gaussian free field. Okay, and the starting point for this is the following definition. So let's suppose that x, this is a simple random walk on my graph G. Then for x, y vertices, I'm going to let g of x, y be the expectation starting from x of the number of times that x visits y up until first hitting the boundary set. First hitting the boundary of V. Okay, and this is the another way of referring to this function is that this is just the discrete Green's function on this graph. And the statement that we're going to try to prove now is that G is what tells you what the covariance of the discrete Gaussian free field is given by. So here's the proposition. So if H is a discrete Gaussian free field on G, then for all x and y in V, we have that the covariance of h of x and h of y, this is just equal to g of x, y divided by the degree of y. Okay, so this gives the covariance function for the discrete Gaussian free field. Now, one thing I want to emphasize is that in the very beginning, when I defined the discrete Gaussian free field, I had a 1/2 in the exponent. And if you look at some other sources, they won't have a 1/2 in the exponent. They'll have something else, like 1/8 or 1/16 or something like that. And the reason for that is that they don't want to write, they're working on something like Z2, and they don't want to divide by D here. And since I put a 1/2 in the exponent in the beginning, when I go to the covariance function, I have to divide by the degree of my vertex. All right. So let's try to prove this in the last 15 minutes. So, okay, let me just remind you that we can write H as this random linear combination of an orthonormal basis of our Hilbert space. So this is an orthonormal basis of h of g, and the alpha i's, these are going to be IID normal 0, 1. Okay, so this was from the very beginning. And what we're going to do now, before we prove this proposition, is we're going to do an easier covariance calculation. So let's suppose that that f and g, these are two functions in our Hilbert space, and let's just write out their series expansions. So I'm going to take f to be equal to a1 times f1 up to an times fn, and g is going to be equal to b1 times f1 up to bn times fn. Okay, so we have our two functions, and what we're going to do now is we're going to calculate the covariance of the Gaussian free field when you take the inner product of it with these two functions. All right, so what are we going to do? We're going to let's do this calculation. So we're calculating the covariance of h inner product with f, that random variable, the covariance of this with h inner product with g. So what is this equal to? Let's first calculate these two inner products. This is the same thing as the sum of the product of the coefficients of these two vectors. So you just have ai times alpha I for the first one. And similarly for the second one, you have bi times alpha I. That's what these two things are equal to. And because the alpha i's are IID normal 0, 1, this is the same thing as the sum of ai times bi, because all of the cross terms are just going to cancel. And this is the same thing as the inner product of f with g. Okay, and this is the starting point of getting the covariance function for the heights of the discrete Gaussian free field at different points. All right, so let me just take a step back now and emphasize some properties of G. what are some important properties of this, this Green's function? So first of all, if x is not equal to y, then the Markov property for our simple random walk this implies that g of xy is equal to 1 over d of x times the sum over all vertices adjacent to y in the graph, all vertices w, of g of wy. And this equation, if you rearrange it, implies that this function g of xy has 0 Laplacian at x if x is not equal to y. And here, I'm always, in the next couple of lines, I'm taking the Laplacian, let me write this in red. This is in the first variable. Taking the Laplacian in the first variable. And similarly, if I calculate gxx, this is just going to be equal to 1 that counts the visit to x while you're at x, plus the expectation of the subsequent visits. And this tells you that the Laplacian of g at xx is equal to minus d of x, if you just rearrange that equation. And finally...
So Jason, is there a typo in part 1? Should it be w adjacent to x as well?
No, I'm doing this all in the first variable.
No, in the first line.
Yeah, the first variable.
No, but the sum should be w neighbor of x.
Oh, right. Yep, sorry, that is a typo. Thank you. Yep, that was a typo. W adjacent to x. OK, good. All right, and then finally, g of xy, this is always equal to 0 if x or y is in the boundary. Okay, and these three properties actually, these completely characterize the function g. All right, now let's look at one more property of g. So one other property that g has is that for all x, y, and v, we have that d of x, the degree at x times g of xy is equal to d of y times g of yx. So this is one other property that that g has, and this is sort of an elementary thing to prove. Just follows from the definition of simple random walk. And since we're getting kind of low on time, and I want to finish the covariance, let's skip the proof of this, and let's just go on and finish the covariance derivation. Okay, so here's the idea. So let's suppose that we have a function which is defined on our graph. Then we can write it in kind of a funny way. You can write f at x as the sum over all y in v of f of y times the indicator of x evaluated at y. So that's one way of writing this. And this is the same thing as the sum over all y and v of f of y times 1 over d of x. And then I have the Laplacian of g of yx times minus 1. I'll put a minus in front. And here, as before, this is in the first variable. Okay, so this is one way of writing the value of the function f at x. And now you can apply summation by parts and write it in an even more convoluted way. So this is the same thing as 1 over d of x. And then you sum over all edges in your graph. And then you take the product of the gradient of f with the gradient of g in its first variable. Okay, so this is how we want to express our function. So here's a shorter way of saying it. We can write h of x. This is just equal to the inner product of h with 1 over d of x and g thought of as a function in its first variable with the second variable fixed as x. All right. And so now let's use this to calculate the covariance. So we have that the covariance of h of x and h of y, this is equal to the covariance where I express h of x and h of y using this formula. So I have h inner producted with 1 over d of x with the same thing but with y. And by our formula from earlier, we know that this is equal to just 1 over d of x, 1 over d of y. And then we have the inner product of g, thought of as a function in its first variable, and the same thing for y with respect to our discrete Dirichlet inner product. And let's just write out what this means now. So this is the same thing as 1 over d of x, 1 over d of y. And then you sum over all edges in the graph. You take the gradient of the first function with respect to x, and the gradient of the second function. And you get that. OK, and then we do an integration by parts, summation by parts, to put the Laplacian on the, I want to put it on the second function. So I have g of wx, Laplacian g of wy, and then I get a minus 1 in front because I did summation by parts. And we're almost done. Let me just finish it maybe here. This last little bit of board. Right, and so what is this equal to? We just have to remember what our formula was for the Laplacian of g. And what you get is that this is the same thing as 1 over d of x, 1 over d of y, times 1 over d of y, sum over all vertices w. And then we have g of wx times d of y. And I've canceled the minus sign already. That came from the summation by parts. It is also present in the Laplacian. And this is, if you just sum this up, what is this equal to? This is just 1 over d of x times g of yx And that's the same thing as 1 over d of y times g of xy. And that's the end of the derivation of the covariance function for the discrete Gaussian free field. And what we're going to do next time is we're going to repeat all of this, but in the continuum. And you're going to see that everything is very, very similar, except for there's some extra little technicalities that one has to worry about, mainly because the continuum Gaussian free field is not going to be a function in the usual sense. And so I'll stop there.